Hello, my name is Serena Wright and today I'll be providing a presentation on yellowfin tuna vertical behaviour and catchability in the South Atlantic. This piece of work was mostly funded under the aottp but also had contributions from the Darwin Plus and Blue Buck programme, so there's a lot of contributors, not only from CFAS but also from obviously St Helena Government, the St Helena Fishermen's Association and Stanford University, so a big thank you to everyone that's been involved. So the aims and objectives of this bit of work will be looking into the local landings of yellowfin tuna and how this can vary in space and time, and then looking into whether we can attribute these changes in landings to bottom-up or top-down pressures. So looking at whether the availability and accessibility of tuna is changing in space and time. To provide you with a brief outline of what we were presenting today, we'll first give a brief overview of the kind of data that was recovered from the electronically tagged yellowfin tuna within the St Helena waters. We'll then look at how depth changed depending on the lunar phase. Next, we'll look at how acceleration can be used to better understand the behaviour in space and time. And finally, we will be linking any of the behaviour back through to the landings and how that changes depending on the time of year. To start off with, St Helena is in the South Atlantic and consists of a key fishing ground around the inshore region of St Helena Island, with two other kind of key fishing areas at the moment, to the west, which is Bonaparte Seamount, and to the north, which is Cardno. So these key fishing areas were used to deploy and recover all of the electronic tags to date. So in total, in terms of the recoveries, we've had 3 satellite tags recovered from yellowfin tuna, which provide a location estimate along with the water temperature, depth, light and acceleration. Those were deployed on tuna between 101 and 125 centimetres and were at liberty between 45 and 232 days. We also deployed data storage tags in the form of CFAS G5s, where we've had 14 recoveries to date, and also low-tech light-based tags, which we've had 10 back to date. So, and those were on smaller fish between 67 and 85 centimetres or 64 and 87 centimetres straight fork length. Okay, to provide a brief overview of the kind of data that is recorded by the electronic tags, the depth information that has been recorded shows yellowfin dove to a maximum depth of 1,014 metres, with 94% of the time spent less than 100 metres in depth. The average water temperature experienced by the yellowfin tuna, 88% of the time it was above 20 degrees, and in terms of the body cavity temperature, 86% of the time it was above 22 degrees, obviously with variability depending on the time of year. To provide an example of the kind of data that we get back from these electronic tags, here's a plot which shows the Julian day on the bottom axis and the hours of the day on the y-axis, so from 0 to 24. So as the year progresses, you can see that the timing of sunrise and sunset should change, reflected in a switch from day to night. If we then plot using one of the recovered yellowfin tuna depth traces, we can see that the depth trace coincides with the switch at sunrise and sunset. So we can see that on average, yellowfin tuna most of the time go deeper during the day, and the switch occurs at sunrise and sunset, reflected in the banding here at sunrise and here at sunset. One of the interesting features of this is during the night, you can see kind of a stripy pattern in the depth, which shows them going deeper at certain times. If we overlay the lunar illumination over the same period, we can see that the timing of the new and full moons coincides when they're going deep. So if we look at that in a slightly different way, we can see the average depth of the tuna changing depending on the level of illumination at night. So we see that the average depth during the night is between 30 and 10 meters deep. And as we get to full moon, the average depth of the yellowfin tuna starts to get deeper and deeper, reflected here in this plot. But how does the behaviour change depending on the time of day? If we then start looking a little bit more deeply into what physical behaviour looks like for the yellowfin tuna, the acceleration, which measures the acceleration in 3 axes of motion for the yellowfin tuna, can be used to better understand whether there are strike events or escape events of the yellowfin tuna. So here's an example of a trace showing the depth at the top of the plot, the pitch angle, so the orientation of the tuna in the middle plot, and finally the MA, so the combined acceleration on the bottom plot. If we look at the pitch angle of this dive, which shows the dive from surface waters down to 200 meters, we can see that the pitch angle is relatively steep descent of the dive, followed by a relatively gradual ascent. And if we then look at the combined acceleration, or the MA, on the bottom plot, we can identify where the fast starts were, so the highest levels of activity occurring. And we can see here that this aligns with the bottom of the dives in this particular example. So if we explore a little bit more about where these facts are occurring in time and space, here is an example plot showing where high acceleration events occur. So on the bottom of the axis we have the time in hours, and on the left axis we have the depth of the tuna from surface to 400 meters. So this is basically all the fast starts overlaid in a given month. So what we can see here is during the night, the yellowfin, all the fast starts tend to be in the surface waters above around about 25 meters, followed by a shift to, at sunrise, striking around about the 100-meter mark, reflecting the kind of depth of the thermocline. And you can see a little tail showing, some fast starts occurring at sunrise and through the day at around about 300 meters in this particular case. If we look at how the depth and the location of fast starts changes throughout the year, we can see that between January and March, so the top 3 plots, most strikes are occurring shallower than 100 meters. I mean, there's that blob of fast start events during sunrise at that kind of surface mixed layer depth. But as the year progresses, so if we look at moving through to May and June, you see a much higher incidence of fast starts at the kind of 300-meter mark, which kind of reflects striking at prey down at the kind of mesopelagic layer. If we then look at the orientation or the pitch angle of the tuna once they're striking, we can say that they're mostly striking on prey that are above them in the water column, so during the ascents of dives. So if you imagine if a yellowfin tuna is down below 150 meters, they're relying on their prey being uplit from above before they then take a strike. So this is quite nicely shown within the plot here. So bringing it all together, if we look at how the behaviour changes by month for the tags that we've had recovered to date, the top plot shows the proportion of time spent less than 100 meters, so in the surface mixed layer depth. We can see that there's the proportion of time spent shallow is decreasing, especially between July and kind of October. If we also look at the behaviour classification, which is the bottom plot, we see that there is diel vertical migration, which is tuna being deeper during the day than during the night, mostly between July and October. So again, showing that deep dives during the day. And there's more reverse diel vertical migration, so the black plots between December through to March, which reflects them being shallow during the day and during the night than compared to the night. If we then look at the mean landings by month for the inshore pole and line fleet, varies between January and December, we can see that the lowest landings occur between August and October, which reflects the St. Helena winter. So if we bring it together and we look at the behaviour of the yellowfin tuna and how this may link to the average landings by the pole and line fleet, we can see that in the months and the periods where yellowfin tuna spend most of their time in the surface 100 metres, we have the highest mean landings. So, for example, here we can see the highest landings were in March, April and May of 2019 in this instance, and that coincides with tuna being above, like spending more than 95% of their time in the surfaced 100 metres. Finally, bringing all this back together, this area of work is basically re-emphasising the importance of using fisheries-independent data to understand fisheries-dependent data. So locally, the availability and the catchability of yellowfin tuna appears to vary depending on the behaviour of the tuna, and reflecting reduced catchability during the winter months, which is linked to changes in foraging behaviour. Thank you for listening. If you've got any questions, I'd be happy to answer them. And there's a number of team members from St. Helena Government on the line as well, which we'd be happy to answer any questions. Thank you.